Today, we are moving from requirements thinking into system specification thinking. Up to now, in the course, you have defined your system, identified requirements, selected methodology based on the 3 units that we have covered so far. And today, we want to answer, how do you represent a system before we build it? That is where modeling comes in. Now, in this particular lecture, we are going to look at 3 perspectives of modeling. We'll look at process, what the system does, data, what the system stores, and last but not least, the behavior. Here we're looking at how the system changes over time. So now a complete system must be understood from all 3 angles. If one aspect or perspective is missing, then the system design is incomplete. Okay. Now, models, ladies and gentlemen, are a central part of information system development. They are not something extra that we add on later. They are part and parcel of the thinking process before actually coding an information system. When we develop a system, we are trying to represent something that exists in the real world. Meaning we want to translate a business process, a service, or an activity into an information system. That real world environment is often a bit on the messy side and also most times quite complex. Now, modeling, ladies and gentlemen, allows us to simplify it so that we are able to understand it clearly. All right. So now a model allows the analyst to represent the critical features of a system without getting lost in technical details, which we explained in the previous 3 sessions that we had. Now, when you are looking at modeling, at this important stage, we're not concerned about programming languages, databases, user interface colors, including the hardware. These are physical concerns, okay, that we're going to look at as we actualize the information system. Modeling separates logic from technology, okay? So now, we can say, as an example, just to help us clarify, we are saying that if we are designing a hostel allocation system, all right, the critical features might be students. We'll look at rooms, of course. We'll also factor in applications, meaning how they apply for the room. We'll also look at the actual location of rooms, okay? Now, here we're going to focus on those core elements first. We do not discuss which database software we'll use or how the interface will look. That one will come later, okay? Now, if we mix those things too early, we will lose clarity on what the system should do. Modeling helps us to focus on the requirements. In short, when we model a system, we are forced to ask, what exactly must this system do? What data must it keep? What must it produce? Meaning, what should it give to the environment? These are key questions. And this prevents us from being distracted by features that are not relevant at the analysis stage. Because many times, students will jump into thinking about coding or interface design much too early in the development process. But if the requirements are not clearly understood, no amount of good coding can fix that confusion. Okay, so modeling keeps us disciplined, right? It keeps our attention on what matters first. Another important benefit of modeling is it's a means of communication. When analysts and users talk about systems, they do not always speak the same language, as was illustrated in other sessions. Analysts may think technically, while users think operationally, what they're able to do. All right? So a model becomes a shared reference point. Instead of arguing in abstract terms, both sides can look at the same diagram and discuss what it represents. For instance, if we show an ERD and say, this is how students relate to courses, everyone can see the relationship. It removes unnecessary technical language and replaces it with visual clarity. So, to summarize, we are saying modeling allows the technical design decisions to be delayed until the requirements are agreed upon. Once everyone agrees on what the system must do and what data it must handle, then the development team can decide how to implement it. That sequence is key in information system development. If we start building before we agree on the logical structure, we risk building the wrong system. So what we are discussing today, ladies and gentlemen, is not just about drawing shapes. It is about creating clarity. It's about removing risks, as we'll explain in the next slides. It's about improving communication, and it prepares the system for structured development. Okay. Now, to build on what we have just discussed, another important idea here is that developing a model does not carry the same risk as developing the real system. When you are still at the modeling stage, you are working with ideas, perceptions. If something is incorrect, you simply adjust. If a relationship is wrong, you redraw it, right? If a process does not make sense, you refine it. There is very little cost involved. But imagine you skip modeling and go straight to building. You design database tables, you write hundreds of lines of code, and then later realize that a requirement was misunderstood. Now, you are not just adjusting a diagram, you are redesigning structure, rewriting code, and possibly starting all over again. That is expensive in terms of time as well as effort. Okay. So models, ladies and gentlemen, gives us a safe environment to make mistakes early. Okay. And another key aspect is that graphical models communicate information more effectively than long written descriptions. If you write 3 pages explaining how a booking system works, different people may interpret it differently. But when you draw a diagram that shows the entities, the processes, and flows, it becomes much clearer. And people can point to a specific pattern and say, this is what I mean. That clarity reduces misunderstandings, right? So now here we are saying that models create a structured way of thinking. They force you to organize your ideas. You cannot draw a relationship between two entities unless you know exactly how they connect. You cannot draw a data flow unless you know where the data comes from and where it goes. So modeling is not just documentation, it is analysis. It forces precision, and that precision is what prepares you for building or coding an information system. When we move into the practical activity, you start seeing where your own system ideas are still unclear. That is very normal in analysis. Modeling exposes those areas so that they can be corrected before you start coding your system. So here when we say coding, construction, we're talking about building, we're talking about the same activity, but I'll be using them interchangeably because specifically in your syllabus, building talks about you creating an actual working model in order for you to apply the skills that you're learning in this course. So that one should not make us to feel as if we're talking about things that we have not yet discussed. Right. So now when we talk about the use of these same models, ladies and gentlemen, we are really talking about what modeling allows us to do during system development. One important role of models is that they help us to focus on the key features of a system while separating them from physical implementation details. At this stage, we are not concerned with how the system will be programmed. We are not deciding on tools or platforms. We are concentrating on understanding the system logically, right? For example, if you are designing a library management system, The key features might include books, members, borrowing transactions, and returns, right? Now, a model helps you to concentrate on those elements and how they connect without worrying yet about whether you will use a relational database or how the interface will look. And these models help us, just a minute, okay? These models help us to investigate system requirements with minimal risk and low cost. When you represent your system in diagram form, you can test it mentally. What do you mean? You can ask yourself questions like, does this make sense? Right? Is something missing? Including, is this realistic? Right? So now, as you are doing that, you are also clarifying the requirements, making sure that you are capturing exactly what is on the ground. Okay. If something does not work, you simply change the model. You have not lost anything except a little time. And that flexibility is extremely valuable in development. Okay. And this process also allows us to verify what we have done. A model helps the analyst to confirm whether they truly understand the requirements. It is easy to think you understand something when it is written in text. But when you try to draw based on the text that you think is okay, then the weaknesses will show, right? You actually realize that you do not know what data is required, or you are unsure about the flow of information, or you cannot clearly define the boundaries of the system. And those realizations are not a problem, ladies and gentlemen. It is progress towards requirements refinement. Because when you have such realizations, it means you are discovering gaps before implementation, before you start your construction. So models serve three powerful purposes. One, they clarify. Two, they reduce risk. Lastly, they confirm understanding. And as we move into specific models, you'll be able to see how each type of model contributes towards requirements clarity. Okay. Now, the first perspective, we're looking at data modeling. Okay. Now, data modeling is a top-down technique which is used to analyze and understand the data requirements of an organization, or sometimes it can be a business area, it can be a department or a functional area, and so on. Now, what this means in simple terms is this. Before we build a system, we must understand exactly what information the organization needs in order to function. Okay? Now, an information system exists to manage data, right? If the data is unclear or it is incomplete or even poorly structured, the system will struggle no matter how good the code is. Data modeling forces us to identify the core data elements of the system. What do we mean? For example, if you're designing a student management system, you need to identify things like student, course, registration, payment, even. Now, these are not features, they are data objects. They represent things that must exist and be stored in your information system. So, data modeling provides the foundation for later database design. It gives us an unambiguous representation of data structures, how they are grouped, and how they relate to each other. Okay. Now, this is again key because ambiguity creates errors. Okay. If you're unclear about what a registration is, or whether a payment belongs to a student or a course, that confusion will appear later in your database design. Okay. So now, another important idea here is that data modeling encourages us to let file design or database design to be driven by data structures rather than processes. Processes may change over time, ladies and gentlemen, but an organization may modify how it performs certain activities, right? That's the changing or the dynamicity of processes. But the core data it manages often remains stable. So, for example, a school may change how students register. It may move from manual forms to online forms, but it will still have students, still have courses, including results. So the structure of that data remains central. And when your data model is clear and aligned with business needs, your system becomes more flexible and easier to modify in the future. So data modeling is not just about drawing diagrams, it is about defining the backbone of your system. Okay. So in the activity that I'll give you on the WhatsApp group, you begin to identify whether each of your functional requirements are actually depends on clearly defined stored data. You will link your requirements to what information is required for that functionality. If it does not, then that particular function or non-functional requirement needs refinement. Okay, so let's look at an example of a data model. Okay, so when we talk about data modeling in practice, the main tool we use is the entity relationship diagram, which we are seeing here. Okay, or ERD. Okay, now the ERD is a visual representation of the data in an information system. And what we can see, it will show us, actually what it is showing us here are three key things. Number one, it is showing us entities. Okay, now entities are the main objects or things of interest in the system, things that we keep information about, right? It is also showing us attributes. There they are. And these are details that describe those entities or properties of entities. Some books will also call them characteristics of entities. Then we'll also see the relationship, the diamond there, right? Now, relationships are just showing how entities are connected to each other. And if you look at the diagram, you notice the rectangular shapes, right? Which was already defined as the entities. Now, these are identified by nouns. For example, student, order, book, as you can see here, customer, course, and so on. So each of these entities represents something that must be stored in the system. Okay? And the lines that connect the entities, these represent the relationship or the association. They're just telling us how the entities interact. So as you can see here, a book contains a chapter, right? Then we also have these. You can see the 1, you can see the N, right? Now those represent cardinalities. How many instances of one entity relate to another. So now, for example, a student may register for many courses, but each registration may belong to only one student. What is important here is that this diagram shows structure only. It does not show processes. There is no time. It does not even show who initiates actions. It answers one question: what data exists and how is it connected? So if your ERD is incorrect, your database will be incorrect. If your relationships are unclear, your system logic will suffer. So when you prepare your own system for modeling, you must ask yourself, what are the main entities in my system? Are they clearly defined? Do I understand how they relate, right? And when you complete the activity for this lesson, you will begin identifying those entities before we formally draw the diagram in the next session, right? And these diagrams, ladies and gentlemen, they force precision. You cannot connect, for example, two entities unless you understand the relationship between them. And that is exactly the discipline we want before we begin coding. Okay. Now, the entity relationship principle comes from the structured approach to system development that became popular in the late 1970s and early 1980s, right? At that time, developers realized something important. Many systems were failing because they were built around processes instead of data, right? So Peter Chen introduced the idea that we should first model the data in a system and then use that data model as the foundation for database design. Okay, so now the thinking here shifted from what does the system do to what data defines the system. That shift was very significant, ladies and gentlemen. When databases began to be widely used, organizations needed a way to represent data clearly before implementing it. And the ERMD provided that structure. It allows analysts to define what entities exist, what attributes describe them, and how they are related. And once that logical model was agreed upon, it could then be translated into a database. The key idea here is stability. Processes, like we mentioned in the previous slide, often change. Procedures also can be updated. Workflows evolve. But the core data of an organization is students, customers, products, orders usually remains. So by modeling the data first, we create a strong foundation. If the data foundation is correct, then the system can adapt more easily when processes change. And that is why data modeling holds such an important place in modern information system development. And this is why in your projects, we begin by asking, what are the core entities that define my system? If you cannot answer that question based on your requirements, then the system is not ready for database design or building at all. All right. And here we end data modeling. We move to the next one. We're looking at process modeling. So we are shifting focus from data, meaning what the system is keeping and how it is structured. Now we want to move on to the next part. So here what we are saying is data alone does not make a system work, right? An organization does not exist just to store data. It exists to perform activities, ladies and gentlemen. And that is why we are now shifting to process modeling. And of course, we don't abandon data modeling, as has been emphasized at length. It has its place. That's why we're saying in the very first part of the lesson, we're saying we model from three perspectives. Okay. So now, when we look at the process model, we're saying that while the data model captures information requirements, the process model captures functional requirements, what the system actually does. Okay. Now, let me just put everything, then we can talk through what the system does. So if you think about your own system, you have written functional requirements such as register student, approve application, record payment, generate report. All these are processes, ladies and gentlemen. And process modeling helps us to understand how these activities occur and how data flows between them. Okay? So now, if you look at what is in front of us here, there's a very important issue that has been raised. Many systems fail because they do not do what the user requires. Okay? And that failure often happens because developers misunderstand how the business actually works. Process modeling, ladies and gentlemen, forces us to ask, okay, what tasks must be undertaken in the information system? In what order, right? What information is needed to perform each task? What information is produced? Understanding the business environment is essential before we start the building process. If your system does not reflect real business processes, it will not solve the problem it was meant to solve. Okay, so at this stage, we are expanding our view. Data modeling answers what information exists. Process modeling answers what activities are performed using that information. I hope we're able to see the relationship. So the work that we are going to have after this session, when you rewrite your functional requirements as clear processes and then identify inputs and outputs, you are preparing yourself to draw proper data flow diagrams. Okay, just remove this. All right, now the process model, ladies and gentlemen, gives us the second important view of an information system, right? I think at this stage, we fully understand the data model and how it captures the requirements, meaning what the system is supposed to keep and so on. But we're just trying to emphasize by saying in the slide that it is not enough to know the information. You must also know what task is going to perform. So the process model, ladies and gentlemen, captures the functional requirements of the system. Okay, do this. Okay, now shows what the system actually does with that information. If the model answers the question, what information exists, then the process model answers the question, what activities are carried out using that information. And both views are cardinal to system development. If we only model the data, we know what exists, but not how it is used. If we only model processes, we know what happens, but not what supports it. Okay? So structured development methodologies emphasizes that modeling has a dual role. Okay? First, during the early stages of development, data and process modeling help the analyst to understand the business environment properly. They force the analyst to think carefully about how the organization operates and what the system is supposed to achieve. This stage is about understanding, not building it. Second, the models later become the foundation for design and implementation. Data model becomes the basis for database design. The entities, their relationships that are identified are translated into tables and keys, as well as relationships in the database, linking one relation to another, right? And the process model, ladies and gentlemen, becomes the basis for program specification. Each process identified in the DFD later becomes a module, a function, or even a component in the system. So modeling is not just analysis documentation, it is also a bridge to information system design. What we draw clearly in the project does not disappear. It evolves into the technical structure of the actual system. And that is why modeling must be done carefully. Remember in our discussion of SDLC, we said that it is like a waterfall because the output becomes the input and so on. So now we are saying that it influences modeling, both understanding, clarifying on the requirements, as well as implementation, how the building itself will be done. I hope we're able to see the importance of modeling, right? So now, okay. So this is an example of a DFD. So a data flow diagram, ladies and gentlemen, just shows us how information moves within an information system, right? It does not show the code. It does not show database structure. It shows logical movement of data. And every DFD has got 4 components or notations, as we'll discuss when we start talking about the models. So, of course, the first one, we have the external entity, like you can see here, right? Now, these represent actors outside the system boundary. They could be users, customers, administrators, including other systems, okay? And these external entities send data into the information system, as you can see there. Then they also receive, okay? So they send data into the system, like as shown there, but they also receive from the system. And the second one is a process, okay? Now, this one takes input, performs logical activity on it, and then produces, okay? So it will receive, work on it, or receives from the other side, work on it, and then be able to give out as well, okay? So, for example, a process might maybe validate a request, right? Calculate a total, or even update a record. Then the next or the third one is a store, like this one here. Now this one represents stored information, okay? So it's an open-ended, it's not closed, okay? Rectangle. Now, this one, a store can be a presentation of a file or database tables and so on. And normally a process can read data from a store or write to. So it can read from or write to a data store. These ones that we defined, we talked about earlier. All right. Then last but not least, we have the actual movement of data. Bidirectional. It can move to and from, right? So here, let's not be very concerned if we don't understand what these particular components are able to do for us. What is the purpose of this is just to give us an example and to explain the components. But in terms of understanding them in order to be able to use them to draw the actual models, that is not the purpose of this lecture. So we're going to have separate sessions just talking about data modeling with the model itself, another one for process, and the other one for behavior modeling. But the idea here is just to give us an idea of what these diagrams or models are, and also the purpose that they serve in relation to modeling from the 3 perspectives. Okay, so now the diagram, just to summarize, it gives us a logical picture of how the system operates, right? So it answers those key questions we talked about when we're discussing information system or analyzing information systems. So here, it is a logical representation that allows us to answer key questions. How does information move through the system, right? It does not describe implementation detail. It describes functional logic. If your functional requirements are clear, you should be able to represent them in a diagram like this, okay? If it cannot, or you cannot do that, then it usually means the requirement is maybe a bit ambiguous or it's a bit vague and needs to be reworked. So just like the predecessor, process modeling forces precision. It ensures that every activity in the system has defined inputs, defined outputs, as well as a logical flow. Okay, so now a DFD allows a structured approach to understanding an information system. Now, what that means is that we do not try to understand everything at once. Instead, we break the system into manageable pieces. Yeah, a complex system can feel overwhelming if we look at it as one large block. But when we divide it into processes and sub-processes, it becomes easier to analyze. Okay. So, like we have mentioned previously, it gives us that clarity when it comes to looking at the requirements, ladies and gentlemen. Now, partitioning, ladies and gentlemen, is extremely important. It allows us to examine one part of the system at a time without losing sight of the overall structure. Okay. And what makes the DFD very strong is that it is graphical. It uses simple symbols to represent processes, the stores, and other aspects that we've looked at. And because it is visual, it can represent complex relationships in a clear and concise manner. Instead of reading paragraphs of descriptions, we can see movement of data and the interaction of components at a glance. Okay? And additionally, the graphical nature of the DFD also makes it a strong communication tool, right? In that it hides the complexities that are actually required for the system to be actualized, right? It allows the analyst, the designer, as well as the users to discuss the system using the same visual reference. This actually helps to reduce misunderstandings, right? And helps to ensure that everyone has a shared understanding of how the system should function. Okay. Another aspect under the characteristics, or what we call a strength in this case, is its ability to work at different levels of detail. Okay? At a high level, we can show the entire system as a single process interacting with its external entities. Okay? And this gives us a broad overview. It helps us understand the system boundary, what is inside the system, and what is outside. Then, if we need more detail, we can decompose that single process into smaller processes. Each of those can be broken down further if and when necessary. So this to move from a general view to a more detailed view is called abstraction. Abstraction allows us to focus on the level of detail that is appropriate for the stage of development. Okay? So in early analysis, we stay at a high level. As we move closer to design, we increase the level of detail. Okay. And another key characteristic is that the DFD specifies the system at a logical level. It describes what the system will do, not how it will be implemented. So for example, a process might be called validate payment. The DFD does not describe the algorithm used to validate it. It does not show programming logic. It simply identifies that validation must occur and that data flows in and out of that process are this and that. Okay? And by staying at the logical level, we keep implementation decisions separate from analysis. And this prevents us from locking ourselves into technical choices too early. What are we going to use? What database? What programming language? And so on and so forth. Those can be done by technical people. So the DFD also focuses on data movement. The relationships that matter are the flows of data between processes and between processes and data stores. So for each process, the analyst must understand what data is required, where that data comes from, what data is produced, where that data goes next. If any of those questions cannot be answered clearly, the model is incomplete. So the DFD is not just a drawing, it is a disciplined way of thinking about how information moves and how activities depend on that information. And that, ladies and gentlemen, is process modeling. Okay. Behavior modeling. So far, we have looked at two perspectives of the system, and we know what the two models do. But now there is a third aspect which is still missing. Neither of the two models, meaning the process and the data model, shows how the system behaves over time. Okay. Now, when we look at process and data modeling, they give us a static picture. That's why we'll say under the specific models that we model an instance in time. Okay, static, as at that time. Those are the requirements in terms of the information required and the process that the system will run. Okay, so if, for the sake of argument, we are calling them static because they will tell us what exists, but not how it changes. What do we mean? For example, an ERD may show an order entity and a customer entity and the relationship between them, but it does not show what happens to an order after it is placed, right? In the real world, systems are not static, they are dynamic. Things change. Events occur, ladies and gentlemen. Data is updated. When we analyze the real world environment in which the system will operate, we must identify the events that occur and the effect those events have on the system. For example, a booking is made. Okay? A payment is received. An application is approved. A product is shipped, right? Each of these events changes the state of data within the system. Static models like ERDs do not show these changes. They cannot represent the dynamic behavior of the system. And that is why we need behavioral modeling. Behavioral modeling helps us represent how data changes over time and what causes those changes. It allows us to move from a static picture of the system to a dynamic understanding of how it behaves in response to real-world events. Okay. So now, one of the main reasons why we develop modern information systems is to provide accurate and up-to-date information for decision making. Today, most systems operate in real time. When something happens in the real world, the system must immediately reflect that change. So, for example, if someone books a flight seat online, right? The system must immediately reduce the number of available seats. If someone pays school fees, students' account balance must be updated accordingly. Now, in order to understand this design correctly, we need to understand not just the data, not just the processes, but how the system behaves when events occur. This is where behavioral modeling comes in. A behavioral model focuses on the states and transitions, right? So, for example, an order entity in an online shopping system. So, we have an order which does not just exist, it changes, right? It might move through the following states: pending, paid, shipped, including cancelled, and so on and so forth. Now, each change from the analysis perspective is triggered by an event. So, for example, payment received moves the order from pending to paid. Shipment processed moves it from paid to shipped. Delivery confirmed moves it from shipped to delivered, and so on and so forth, right? Itainasamba moto. Important. Oh, I did. Nimbuze viyo mwana. Okay, so I went offline briefly. So we continue. So we're talking about some examples. So for example, delivery confirmed moves it to from shipped to delivered. So a simple behavioral model often represents as a state transition diagram, right? Under unified modeling language. So this one would show the order in different states with arrows showing which event causes the transition from one state to the other. And this kind of model answers very important questions. Can an order be shipped before payment? Can a delivered order return to pending? Can a cancelled order be shipped? So now, without modeling these transitions clearly, the system may allow invalid actions. Okay? I hope the concepts are making a bit of sense. All right, let me give another example. Let's look at an example from education, right? So I have a student application entity whose possible states can be submitted, under review, maybe approved, even rejected, right? So the event review started moves the application from submitted to under review. The event decision made moves it to approved or rejected. If we do not define these transitions clearly, the system might allow someone to approve an application that was never reviewed. So behavioral modeling protects logical integrity. Just as the ERD protects data structure and the DFD protects process flow, behavioral model protects time-based logic. It ensures that the system reflects how the real world actually changes. Okay. Now, what is the significance, ladies and gentlemen? So behavioral modeling becomes especially important, ladies and gentlemen, when we consider how modern information systems operate. Okay. Today, systems are expected to reflect the real world immediately. Users expect up-to-date information at any moment. And when you check your bank balance at an ATM, you expect it to reflect the most recent transaction. When you book a ticket, you expect seat availability to update instantly. When a student pays fees, their status should change immediately. This expectation means that systems must respond correctly to events as they happen. And this is where behavioral modeling comes. It helps us to design that responsiveness. So if you're looking at a library borrowing system, the book entry does not just sit in the database, it has states. It may be available, issued, overdue, reserved. And when a student borrows a book, the event of borrow book changes its state from available to issued. If the return date passes without the book being returned, the event due date passed may move it from issued to overdue. When the book is returned, it transitions back to available. A behavioral model such as the state transition diagram would show the book entity in these different states, with arrows indicating which event causes each change. So this model ensures that the system does not allow invalid transitions. A book that is already issued should not be issued again unless it returns to available. So without behavioral modeling, we might correctly design the data structure and correctly define the processes, but still allow logical errors in how the system behaves over time. Behavioral modeling also helps identify event-intensive environments, systems where many changes happen frequently, right? So like banking systems, for example, airline booking systems, e-commerce platforms. In such environments, data is constantly being updated. If state changes are not clearly defined, the system can easily become inconsistent. Behavioral modeling ensures that events are identified early, valid transitions are identified and defined, invalid transitions are prevented, sequence of actions is respected. Right. So just as the ARD gives us structure, the DFT gives us flow, behavioral modeling, ladies and gentlemen, gives us controlled change over time. And in modern systems, that control is extremely essential. So actually we can try to wind down, though we'll go have another slide which will summarize everything that we have talked about. But as we summarize on behavioral modeling, when we talk about behavioral modeling, ladies and gentlemen, we're really talking about understanding change in a controlled way. Okay. Some entities in a system are relatively static. They do not change often. For example, a course entity in a school system may remain largely the same throughout the years. But other entities are dynamic. They change frequently because events constantly affect them. Think of entities like order, booking, application, payment, registration. These are event-driven entities. Every time something happens in the real world, these entities change state. Behavioral modeling helps us identify what events exist in this environment, what effect does each event have, does the order of events matter? Those are key questions. Okay. So, ladies and gentlemen, we're trying to just emphasize the fact that the sequence of events matters because that will also feed directly into how the actual implementation or building of that system is going to be. Behavioral modeling forces us to define these rules clearly. It helps us identify intermediate states. Sometimes a record sits in a temporary state until certain conditions are met. If we don't model that, we may allow inconsistent operations. And this is very important in event-intensive environments. Okay, let's use an example. In an airline system, seats are constantly being booked and cancelled, right? So now, if we don't model the sequence, you may find that seats that are not available may appear as if they're available, and vice versa, right? Or in a banking system, transactions occur frequently, right? And without behavioral modeling, the system might technically function, but it will not reflect the real world flow correctly. So when we combine all three perspectives, data model tells us what exists, process model, what happens, behavior, how things change over time. And together they give us a complete understanding of the system before we build it. And that is exactly why in the activity you complete, you examine your own system from all three perspectives, even before we start looking at drawing the diagrams. Because once your logic is clear in these three perspectives, the transition to design, where we look at the interface design, and later on coding becomes structured and manageable, ladies and gentlemen. So how do we summarize? Just a quick recap. We have looked at why modeling is necessary, right? And its role before we talk about the actual information system building. So modeling is not just about drawing diagrams for the sake of it. It's about thinking clearly before implementing. Okay? So data modeling captures the structure of the system. It defines what entities exist, what attributes describe them, and how they relate, meaning the relationships. Without a clear structure, database design becomes unstable. Then we moved on to process modeling, ladies and gentlemen. Here we're looking at functional flow of the system. It shows how data moves from how activities are performed and how inputs are transformed into outputs. Without process modeling, the system may not reflect how the business actually works. Okay. Then we ended with the behavioral modeling. Here we're saying it captures how the system changes over time, right? It identifies events, states, as we discussed, and valid transitions. Without behavioral modeling, systems may allow incorrect sequences, including invalid operations. So when we combine these three perspectives, we get a complete logical understanding of the system. And only after that logical understanding is clear, should we move to design and implementation. Okay, so now let's look at the activity that will be shared on the WhatsApp group. So since we know the role of modeling in information system development, the activity I will share is going to ask a number of key questions. Now, the aim of this activity is just to ensure that we're doing the right thing and that we have clear requirements that are responsive to the business area that you're looking at. So there are a number of questions in the activity that I'll give you. But again, as you go through, there are some key questions that you should be able to answer on your own, and the answers will be specific to the system that you are considering for development. So for example, does your system stand up to this structure? It is one thing to understand modeling in theory. It is another thing to apply it to your own project. So the worksheet that I will share is about completeness of your requirements, not necessarily that it is a test, no. Okay? So it is a preparation exercise. It will help you to check whether your functional requirements are supported by real data. That's very important. Whether your processes have clear inputs and outputs. Whether something in your system changes over time and whether you understand how it changes. Whether your first build is realistic and manageable. Right? Those are key issues. And if you find gaps, if there's a no to any of these, that is progress, like we mentioned in the session. It's a point for you now to revise, to reevaluate, to clarify. All right? Now, we are not just going to draw formal ERDs for the sake of drawing. They are supposed to be a reflection of what the system is about. But in this particular activity that I'm sharing on your group, it is not supposed to lead you to draw the actual diagrams. We haven't learned how to draw the diagrams yet. We just know the notation, we know the flows and so on. But it's just to help you to ascertain whether the requirements are clear, whether the data for those requirements is apparent, whether the transforming activities and so on, other key aspects that we have discussed are also clearly indicated. In short, it is a point for you to start clarifying your requirements. So that even as we move on to the actual drawing of the diagrams, meaning the actual design, you have requirements that are able to stand the test of time and also reflect what the system is supposed to do. And once you complete this reflection, then you'll be in a much stronger position to actually convert your requirements into an actual model. Okay, so I will share the worksheet on WhatsApp. For now, we'll end here. Thank you for your attention.